Welcome back, everybody. We're starting a new series of video topics that I have starting with the letter D. D for dynamics, which is kind of a word for force and things related to forces. That's our broad topic in this next set of videos. Now, the difference between this and the last set of videos is when we're studying motion, learning about velocity and displacement and acceleration, all of that was us describing motion, right? We were looking at objects that were moving and trying to describe them. This next set of videos, and to be honest, pretty much the rest of the AP Physics 1 course, is us trying to understand what causes motion and what causes motion to change. So not just saying an object is accelerating, but why might something be speeding up or slowing down or turning left and right? That's what we're getting into here. Now, we're starting off with Newton's 3 set of laws about motion. This first one is still kind of about describing it, but again, with Newton's laws and getting into energy and rotation, things like that, we're going to have a better understanding of what's causing this motion to begin with that we've done a good job describing in our last series of videos. So starting off with Newton's first law, maybe the easiest, but it's a bit of a mouthful when we look at the definition. Here's what it says. An object at rest will remain at rest, and an object in motion will remain in constant straight line motion, unless acted on by an unbalanced, a net, or sometimes I like to say an interfering force. Now, we haven't yet talked about this word force in this class, but you all probably have a pretty good idea of what a force is. If you need a definition, think of a push or a pull. Either of those two things, that's an example of a force. So as long as nothing is pushing or pulling on something, that's what they mean here by unless. So as long as that's not happening in an interfering, in an unbalanced kind of way, well, this first fraction of a sentence holds true. Let's look at it. The first part, objects that are at rest, stay at rest. That's probably not surprising. Okay, your TV monitor or your laptop monitor, your computer monitor, whatever, okay, it's at rest right now. It's probably going to stay at rest unless you shove your computer or there's an earthquake or your kid brother or sister knocks it off. All of those are interfering forces. But things that aren't moving stay not moving. We experience that all the time. But also, and this one's a little trickier here, it says an object in motion will remain in constant, so the velocity or the speed is staying the same, and it's moving in a continuous straight line. So really, the velocity is staying the same. And that's a little weirder because we see a lot of examples in real life. Think of a Hot Wheel car. Think of a ball rolling, across the grass. Objects tend to slow down, right? They roll and then they slow to a stop. But that's because there's this unbalanced interfering force like friction, which we'll be getting into. If we could remove all these unbalanced interfering forces, air resistance, friction, etc., once I get something moving, it should stay in constant straight line motion. To be honest, gang, we've already made this assumption. Remember our projectile motion? We said horizontally, those objects are moving at a constant velocity. The reason why is this first law, this first idea from Isaac Newton. Okay, if there's no air resistance, things that are moving will stay in constant horizontal motion. Okay, in that horizontal sense. Now, I have this kind of silly looking diagram, and this certainly is not a perfect example of physics in all shapes and forms, but it shows this idea of Newton's first law in pretty good detail in a couple of levels. First, let's look at this skateboard. We kind of have like this chemistry beaker riding this skateboard. The skateboard starts off moving, and it continues moving to the right until it hits this rock. Well, this rock is applying a pushing force. It stops the skateboard. This skateboard would normally just continue moving in a constant straight line forever. Okay, I'm going to kind of reset my diagram. Oh, it's not going to reset. Hold on. Okay, it's reset right now. So the skateboard would keep moving until it gets hit by a rock. There is a force. And also the beaker, okay, this test tube. Even though the skateboard stops, the test tube was moving. It wants to continue moving in straight line motion. That's why you tend to, continue moving after, say, you're riding on a skateboard and it comes to an abrupt halt. That's Newton's first law. You keep on moving. Of course, then you're flying through the air. Gravity starts pulling you down. Now, technically, this rock maybe isn't a great example because the skateboard pushes on the rock. According to Newton's first law, it shouldn't remain at rest, maybe unless it was like glued to the floor or something. But again, not a perfect idea or example, but it gets the point across. Now, this is related to something known as inertia. All matter in the universe has this property known as inertia. And inertia, it's the tendency, it's almost like a desire to want to either remain at rest or, this is also Newton's first law, or remain in straight line motion. Inertia is about not wanting to change. It's kind of like laziness. If an object's at rest, if you're sitting on the couch and you're lazy, you want to stay at rest on the couch. But also, if you're moving on that skateboard, you want to continue on moving unless something gets in the way, like a rock or, say, friction. So this is very much related, this term inertia, very much related to Newton's first law. It is often referred to, in fact, as the law of inertia. So inertia is this property that objects have in our universe that want to continue to either remain at rest or continue moving in a straight line. This also relates to something called mass. Mass is actually how we quantify inertia. Just like we have this kind of vague thing known as distance, how do we quantify distance in this class? By maybe measuring in meters or centimeters or kilometers. Mass, something that we're going to measure in kilograms, that's how we quantify, that's how we measure inertia. Things with more mass, like a train, has more inertia. It's very difficult to stop a moving train because you might say it has a lot of mass. It has a lot of inertia, a lot of tendency to remain moving. Okay? Now let's be very clear. Mass is not weight. We'll talk about weight a little later. Weight is due to the force of Earth's gravity pulling you down. Inertia, this tendency, this is universal. You have inertia. Objects have laziness anywhere in the universe. Weight is due to a force from, say, the Earth. So mass and weight are not the same thing. Weight and inertia are not the same thing. Mass and inertia, these are universal. Take 1 kilogram to Mars, it's still 1 kilogram. It's still lazy. You still have to apply a pushing force to get it moving. Weight is a force that has to do with usually here on Earth because of Earth's particular gravity pulling on it. So make sure we're aware of that. Sorry if this is getting cut off a little bit. It just says weight is due to gravitational attraction between things. And we'll get into that particular type of force a little later. But okay, Newton's first law, it describes how things that are at rest want to stay at rest, things that are moving want to keep on moving. Okay, very similar to this term known as inertia. That's this quality, this property that objects have. And how do we measure inertia? Using something known as mass. And we'll be elaborating on this in class and in future videos. But that's it for this one. Newton's first law is just describing this tendency of objects and how they want to move. So long, thanks for watching.